Alright, I'm going to be determining the rate equation from the given information over here in the table. It's for mercury chloride with oxalate, I think it's oxalate, and then to chlorine, CO2, and mercury chloride. So in this problem, we're just going to focus on the reactant side, of course, which is typically how we do these. And we're going to compare the experiments that we can actually hold and control while noting which one is changing. The one that's changing is going to be the one that allows us to do the math we need to do in this problem. So let me go ahead and get this set up. Okay, so in the first experiment, you notice that these two right here are not changing, but these two are changing. So you're going from 0.10 molar to 0.2. So what do we need to do? Well, and we notice that also this is changing as well. So we need to set up our rate equations for each of these experiments. So for the first one, I'm going to let the rate 1 equal R1, which is equal to the concentration of the mercury chloride, and the oxalate being 0.10. That's the first rate, equal to 1.3 times 10 to the minus 7 power, the initial rate there. And then for your second rate, the second experiment's rate, it was equal to 5.2 times 10 to the minus 7. But as we notice, our concentration is changing for oxalate, but not chloride. So this is your control right here. The one that we can actually control in this is the one that allows us to simplify the math and do like a single variable equation is by holding one of these constant in the lab, right? So for experiments 1 and 2, your control are going to be these two values because they don't change at all, respectfully. That's your control. But you know what's changing, and we can do the math on that. Let's go ahead and see how it works now that we have these two equations. What you can do is you can actually look at the ratio of the second experiment's rate over the first experiment's rate, which I denoted over here. And then I held my my rate 2 equation and rate 1 equation, mercury chloride here, to be constant. You're just taking the ratio of these two things and these two things. And from that ratio, you got a ratio equation where you can solve for what you don't know. So in this case, this is going to be 0.20, 0.10, and we can cancel out the part of this that isn't going to matter at all, and that's going to be this one right here, respectfully. So let's see what we got here. Yep. All right. Let's set that equal to this. Now I'm going to go ahead and calculate this value right here. So 1 second. Okay, so that'll give me 4 for this expression here. Okay, now that we have that, we can cancel what we don't need, our control, right? So I'm going to go ahead and cancel those two. And this will allow us to just really look at the proportion to the nth power of this. Now, by the way, this is 2, 0. Now, what you can do is you can use a law of exponents for this step right here. And you can just roll these two equations here into one exponent using the distributive property, right? So from here, now all I need to do is simply this. I'm just going to go ahead and say that that's this over this, and we can take that nth power out, which is the whole objective of this, and it turns into a single variable in n. Now you just take your natural logs on both sides. That's going to be 1 into 2, that's 2 twice inside the parentheses there, and you'll have your n is equal to ln of 4. Drop the n down using a property of logs. then you're going to have that n is equal to ln of 4 over ln of 2. So that's equal to 2 here. We're basically going to be repeating the same thing for rate 3 compared to rate 2. And if you look at rate 3, it's set up like this. You're going to have this. Change my color here to be consistent with this. So then we're going to go ahead and plug rate 3's values in this now, and we're going to solve. But I want you to notice the control already here. This is changing from that to that, respectfully. So we're going to use that for our change, and now we're looking for n. Using the same math, guys. We're just holding this in control over here now. Now this becomes the control. These two values, so to the right, to the nth power. So then, let's see what we can do here. Let's go ahead and cancel those out, and let's work on it. Let's go ahead and put all our rates in here. Now let's do the math. Now remember, they're both to the n power, so we're going to roll them into 1 power of m. Now let's go ahead and get the ratio of that. Okay, for this one, I'm not going to lie, whenever I did the math on this one here, I'll make this clear. I definitely got 1.92. But you can just this is close enough, right? Let that approximate to 2 there. Let's see if hopefully that doesn't change too much, but we should be okay on assuming 2 since that's so close. It's kind of like when you do empirical formula. So now that we have this here, let's write it out and finish this off. Take our natural log on both sides, drop our power of n. That becomes, oops, sorry, ln of 2 down, and just guys, again, 0.10 into 2, that's going to give you 2 there. So for this one, it actually looks that m is equal to 1. ln of 2, they're just numbers, they're the same thing, m is equal to 1. So we've definitely found our rate equation for this. Let's go ahead and write that down. Okay, so for m earlier on, let's see, m and then n here. For m we got 1, which that's going to correspond to that, which is the magnesium chloride. And then for n we got 2, and that's going to correspond to the change of oxalate that we got over here. So the change for that one was experiment 102 for n, which is we actually did that one there first, and then the second experiment was modeling this change. So we're going to go over here and we're going to put it down. And we're going to calculate k. That's the last step here. Okay, for this one, we're just going to calculate k, so I'm going to go ahead and do the math real quick. Okay, so just multiply your 0.10 and your 0.10 squared. That's going to give you 0.001 times k. So once you do that, you divide 1.3 times 10 to the minus 7 by 0.001. You get that k is equal to 1.3 times 10 to the minus 4. So 1.3 times 10 to the minus 4. Hope this helps.